things the same. Two walk like two out the door. Then you have magic. One comes around, one today. They don't see things the same. Two walk like two out the door. Then you have magic. Then you have magic.
Today, we do have a couple of talks and a set of lightning talks that will take us up to lunch. After lunch, we will drop into the witness breakout session, have a break, and then in the last session of the day, we'll be getting the laptops out and doing any code dives or exploration together in small groups. If you have suggestions for birds of a feather topics for that section, there's a whiteboard. You can scribble them on the back or grab a Post-it note, stick it on, and we'll try to gather people based on common interests. Okay, so but this morning we are going to kick off with the summaries of the 3 breakout rooms we had yesterday. So we'll go with certificate transparency first, then binary transparency, and then a summary of the key transparency room. So first up for certificate transparency, I'd like to invite Joe to the stage.
Good morning, friends. So yesterday we had, I think, quite a productive breakout for CT. We started out with Devin leading a conversation on how we could adapt CT to a post-quantum age. The key observation here is that post-quantum algorithms are going to result in much larger keys and signatures. And our current approach to TLS has been to sprinkle signatures in essentially wherever it was convenient for us, including in CT. And so that results, if we naively swap in post-quantum algorithms for our existing algorithms, we're going to balloon substantially the size of the TLS handshake and also logs themselves, but by something like 8x, so pretty substantially. There are some knobs we can tune here, but all of them have some sort of size compromise. Like you can't get it for free. And this was combined with combined with the expected significant reduction in certificate lifetimes is going to result in even more issuance for that logs are going to have to deal with. So a lot of this conversation was just like, how do we deal with that? There's a lot of uncertainty in the precise timelines for PQ, but the reality is that the Web PKI is under a lot of pressure to start moving in the PQ direction right now from regulatory agencies, and there's critical mass there. And I think there's interest in making sure that we have a crisp story for CT, because the fear is if we don't have a crisp story for CT, that transparency could in fact be sacrificed at the altar of making TLS handshakes smaller. So it behooves us to think about this now, even though it's probably on the order of maybe 10 years out concern in terms of actually like needing post-quantum algorithms. We had some ideas that popped up that might help us to mitigate the impact on the handshake. For instance, that maybe transparency data doesn't actually need to be included in the handshake itself, but we could provide it out of band. And then, like, once we knew that a certificate was not included in a transparency log, we could interrupt the connection or something like that. Obviously, that's not without sacrifice, but it was a design space that was at least worth considering. The observation was made that the current shape of SCT auditing actually can be relatively straightforwardly adapted to check for certificate inclusion even without SCTs. So if you're willing to make the sacrifice of like initial connection, we have things that sort of look like what you'd have to do, but they're gross for various reasons otherwise. So while no brainwaves popped up for how to solve the challenge during the breakout, we did spend a lot of time identifying ways that we could mitigate the size impact for logs. Actually, we spent a ton of time in the breakout on that, both in the PQ portion of the conversation and in the portion that followed. The first big observation we had here is that if you're a log operator, your costs are dominated by consumers pulling down the contents of the logs, but that many consumers of CT logs in particular don't actually care about a lot of the data that's in the CT log, and also don't frankly trust the log. So they're not interested in verifying necessarily, and that there's an opportunity there for literally just adding like some read endpoints that let you pluck out just the data you were interested in, and on the theory that for a huge number of consumers, that could result in a dramatic reduction in the data that they would need to pull from the log, and they'd still be just as happy. So that's an interesting one for me personally, as someone who thinks about CT in today's terms, not just for a post-quantum transition, because that's something we could do now and get some benefit from too. So we briefly chatted about the impact of CT on logs, of PQ on the size of the CT logs keys themselves. That got us off on a brief conversation about logistical challenges of log management and whether there was an opportunity to centralize and standardize log metadata to make it less labor intensive. One of the things I was complaining about in my talk yesterday was just like the amount of logistical overhead of dealing with logs coming up and coming down. So if there's a way we could sort of streamline that. Let's see. Had a bunch of good stories from the beginnings of CT, which is worth not reading out here, but was fun notwithstanding. There was a lot of discussion about what we could do if there was a dynamic that we could have where adding a CT log could reduce the burden in a meaningful way on the remaining CT logs. Because right now we have this property where if we add a log, it increases our redundancy, but there's enough cross-logging that it doesn't, like the life of other log operators doesn't get easier. And so how might you sort of play with that space? Obviously right now we do temporal sharding, but we could also do something like namespace sharding. So, the example from yesterday was .mobi domains are only going to get logged to these logs, and then dot whatever domains could be logged over there. Obviously there's some work you have to do there to make sure that you load balance, because .mobi is tiny versus some .com or something, but not necessarily none of the ideas we came up with there I think were fully formed or brilliant ideas, but they're all, what we did do is identify a bunch of design spaces that are worth thinking about more. Let's see. After we finished the PQ brainstorming, in the same conversation, we also chatted a bit about other ways we could reduce storage space for logs, which is, for instance, coalescing common intermediate data across entries, which is a proposal that's been floating around in CT for a while, and I think its time has probably come. Yeah, let's see. Okay, we had a whole nother conversation about what does the world look like if we have a bunch more CT enforcing user agents, because we have that coordination overhead problem where Apple and Chrome and hopefully Android and Firefox and whoever else could all need to stay in line together. I think this conversation ended up being a little bit more straightforward, because I think the reality is that this community is filled with people who want to do the right thing, and so there's a lot. It's a very strong incentive to sort of stay relatively well aligned, which doesn't make this problem easy, but it's of the challenges we face in transparency ecosystems. It's not actually the worst of them. Let's see what else. What else? We had a lovely conversation at the end about auditing, SCT auditing, and whether the world is going a little bit more into depth on some of the topics that Lena was chatting about in her talk, and whether there were design changes we could make to the CT ecosystem that might facilitate better matching PIR schemes in the future, so that we could increase our coverage of SCT auditing. This is a little bit of a complicated space, and so I don't think we had any brilliant ideas there necessarily, but Lena reiterated the value of having dense indices, which come from tiled logs, being quite helpful for this space. That was an interesting conversation as well. And I'm probably forgetting something huge here as I scroll through the notes, but I think that's a pretty good overview of what we chatted about. So, yeah. Actually, I've got 5 seconds. Is anyone who was there who's like, "Oh, Joe, you're forgetting something important"? Now's your chance to like scream. It's like, "Oh, you fool! We also talked about X." Oh, all right, I'll take it.
Sounds like you covered it.
Thanks.
Thank you. And yeah, I did hear a lot of laughter coming from that room, so it sounded like you're all having fun. Okay, can I get Hayden up next to cover the binary transparency room? I've got the BT. Great. Thanks, Hayden.
William's also coming up because he took wonderful notes. Thank you, William. Let's see. So where we started with BT was trying to first find some commonality across it, because BT is an umbrella term. And very quickly, we realized that there are many different types of binary transparency projects. We discussed firmware transparency, signature transparency, system transparency. And to be honest, I don't know if we had any really concrete action items that came out of this, but it was a very enlightening discussion to see that there's just a lot of different forms here. And maybe at some point we'll find some commonality between these and find opportunities for alignment, whether it be due to schema or other parts of transparency. Yeah, I'm trying to think of specific ones. There was a lot of discussion around system transparency and runtime transparency as something that seemed an area where there's a lot more opportunity for exploration, and also something that was a combination of other transparency systems as well. There was some discussion around how can you combine what I think, William, you referred to as artifact transparency, which I think typically we're referring to as just binary transparency, with other parts of transparency ecosystems as well. We had some discussions on specific use cases. We tried to propose a set of claims. I don't know if we actually ended up proposing a set of claims, though.
I think there was consensus that the claim set should be, minimal, falsifiable, per Al's sort of maxims around it.
I think one very, very clear application was binary transparency within package registries. So we had some discussion on PyPI and got William's thoughts as well on that.
One log versus multiple. One thing we discussed was the relative importance of each ecosystem or each use case running its own log versus one sort of giant log to rule them all. And the trade-off we discussed there was, the operational complexity of running a log is going to go down over time, especially with these next generation logs. However, there's still going to be a wide range of community interest and technical ability behind, or that determines whether or not, for example, a smaller packaging ecosystem can stand up a log. And so one thing we discussed was, does it make sense? How do you authenticate to a log? Is there a difference between authenticating versus submitting a signed payload, et cetera? Those are things that we still need to, I think, sort of flesh out, but those were interesting.
We had some discussions around signature transparency, some discussions, again, around commonalities and differences. There was some discussions around data formats, around aligning on different types of schema. Again, I think the takeaway there is we have a few different approaches, and especially when you're looking at what is the intended use case, that's where some of these differences arise. And we'll just keep iterating on this, come back in a year, see where there's more commonalities and differences.
Yeah. I guess another prominent theme was the question of, so by default, almost everything we talk about is offline, but there's a question of how long do users actually expect an attestation or some commitment to actually live. And so the question of, does it make sense to have a time to live or similar piece of metadata somewhere encoded in the log? And there was lively discussion around that.
While we're looking, anyone else who was in the room, was there anything else that you wanted to call out? We got a good summary.
My
All right,
handwriting
well,
is terrible, so he can't read it.
That's all right. My handwriting's terrible as well. Yeah, I feel like that was about it. Again, like summarizing, we discussed a lot of different areas of binary transparency just because there really are a lot. And honestly, I think it's what makes it an exciting component of transparency, that there are so many different applications and use cases. And I suspect we're going to come back in a year and there will be even more possibilities.
Mm-hmm. Yeah. Oh, I guess one last thing I just remembered was we talked a little bit about the value of algorithmic diversity in the log. And so 6-store goes one way, which is to say, the client has a set of algorithms that they support or suite they support. We should support those within reason. And then 6M is the polar opposite, where we say, here's the one good suite we support, stick to that. And there's obvious trade-offs to both from the client side and from the application side or the server side. But it was a subject of discussion.
All right, so we got.
Great, thank you, Hayden and William, for trying to pin down a very nebulous space. That was a great summary. Okay, up next, I'll invite Jason to talk about the key transparency breakout.
That photo has real, action shot vibes. I don't know if the room was quite that exciting, but, I'll take it. So we had a good conversation with a mix of key transparency log operators, log auditors, and others interested in the space. So I want to say thank you to everyone who participated in the conversation, as I think it was a really good conversation and mix. We had a significant amount of discussion around the role of the auditor in key transparency systems and whether, given the size of logs, there functionally could be public auditing. I think folks in the room were surprised by how large these logs can get, particularly at for the end-to-end encrypted messaging case. And so we explored some ideas, including whether it'd be possible to audit arbitrary sections of the tree or do things so you didn't have to pull down, large, keep thinking large and then go larger amounts of data. And really sort of honed in on this idea of auditor as important and sort of an unsolved part of the OWL. In the second session, we discussed some of the more user-facing components of key transparency. Part of this was about sort of you want to always enroll your keys in key transparency, and you want to have clients monitor themselves, but you may not want to always warn them, and you may want to make the warning be opt-in for a variety of reasons. And so trying to reason about that and how you reason about that across different use cases, as I think one of the things that was interesting that came up was I think we've talked a lot about key transparency in the end-to-end encrypted messaging or email case, but not necessarily so much in the machine identity case, where you have different set of users, different set of sort of failure conditions, and how you would want to warn in those instances. Talked a bit about where standards components or infrastructure would be useful. From the conversation, it seemed like implementation specific of each messaging platform makes leaf node data structures application specific, but there may be standardization around other data structures and things like witness protocols. We talked about how if you can get publishing epochs sufficiently small, you may actually be able to get away with getting rid of SCTs, SMTs, but that was sort of a how do we make the logs efficient discussion? Is that something that's still being worked on? And Filippo led us in a conversation around what could we build as a sort of tiny key transparency server for a small client, and what that might look like, and where I think there was sort of an interesting thought design of sort of taking what we know for big systems, how do we build a small efficient one? In terms of what folks wanted to take away from the summit for the key transparency session, can we find ways to drive down epoch size as a community to simplify the story? Auditing being required to complete the transparency solution, but it's hard to get the incentives right for a third party. And binary transparency in clients. This was considered key to completing the transparency solution, but it's not currently implemented on any of the existing platforms. And so, I think there was one point where sort of given that this has to be opt-in, given that you don't have auditors, there was sort of a discussion of like, is it worth it? And the answer was yes, because you mitigate a number of the risks. Can I say who said like it's a good idea to kill the top 5 risks if you can? All right. So like Bailey said, Chatham House rules. I want to like respect that. Bailey made the point that like if you can knock down the top 5 risks in your risk analysis, then it's worth doing, even if there's still tail risk that you can't converge on, which I thought was like a good message in terms of how to think about security privacy risks in general, and particularly this space where it's, in key transparency, things are new and evolving, and we know we are somewhere between the 2 circles and the owl, but exactly where I think is TBD. Folks in the room, is there anything that I'm missing? Okay. In that case, I'm going to hand it back to Tracy.
Thanks very much, Jason, for giving us those key takeaways. Okay, thank you very much to everybody who summarized those breakouts, especially because I know many people wanted to be in multiple places at the same time, and it was hard to choose, and you all chose well. All of them were very well attended, and lots of good discussions, and I had a lot of feedback from various people that it was really open, and they really appreciated the frank discussions that were happening. So thank you all. Okay, so switching tack now, we are going to call up our next speaker, who is going to be talking to us on the very interesting topic of AI model transparency. So I ask Mihai to come get set up. Killed it. That's a vibe. Okay, just as a reminder for this afternoon, great, thank you. We'll be having a witness discussion session after lunch, and that will take us to the mid-afternoon break. And then for the final hour from 3 to 4, we will be having Birds of a Feather session, which is a chance to sit down with folks from the Trust Fabric team, from the SIGSUM team, and talk about specific topics, dive into code, whatever folks who are sticking around would like to do. So you can feel free to post something on the whiteboard there, or just chat to folks and we can self-organize.
Just checking, is the screen?
Okay, I think we're all set. So, yep, please give a warm welcome to our next speaker, Mihai.
Hello, thank you everyone for having me. I'm Mihai Marusak from Google Open Source Security team, and I'll talk about how we can use transparency for AI, basically how we can start signing models, and this would pave the way for transparency into the entire supply chain for AI. But first, let's begin with what is the problem. So let me put on the malware hack. I'm a malicious user now, and I want to attack some other people using ML. So I know that at some point they are going to use some models. So I trained 2 different models. One, let's call it evil model that contains malware, and another one that is a chatbot that is trained on 4chan, on other media. And I want the users to use these models. Of course, the users are not going to get the models from me directly, so I need to upload the model to a model hub. And when I do the upload, I need to write something in the model card. And because I want the users to take the models, I'll write some fake descriptions. I'll say that the first model is a model that can help you in detecting the malware. Of course, once you use the model, you'll have malware, so you kind of detected it. And the second one is a friendly chatbot. Depends on how you define friends. Of course, users are going to also look at the model name, and they are not going to pick the model based on just the model card. But that's easy to fix. I can just change the name, And now the user, I'm just going to change the name, and now the users are just going to pick the models because they sound useful. So without transparency into how a model has been built, there is no relationship between how the model looks into the model hub and how the model has been trained. So that's what we want to solve. And now let's look at how the model is trained. So in general, when you start an ML pipeline, you start with datasets. And in more advanced cases, you don't start with just one dataset. You do a lot of operations on the datasets. You take one dataset, you run some operations on it to clean the data, to remove invalid rows, to remove information that shouldn't be into the model. Maybe you combine multiple data sources together. You could use human trainers, or you could use programs, software to clean the data. So it's a lot of processes. It's a very iterative process here. Then you select some ML framework like TensorFlow or PyTorch, and then you write some code to combine the data sets and the model architecture, and you combine everything together to train the model. And now finally we have one model, which we can put into storage. So let's say to some model hub. And from here, we can either deploy the model to a production or take it back and continue training on it. So maybe, for example, when you do LLMs, you train a big model on a large data set, but this model will only understand text. But now to make the model useful for specific scenarios, you take the model and you fine-tune it for the specific tool cases that you need. So you take the model from the hub, you train it a little bit more, you put the new version into the hub, and you repeat this process iteratively as many times as you need. Or maybe you want to deploy the model to an Android device or to a phone. In this case, you cannot take the big models. You need to quantize the models. So you convert all the floating point weights to integers to be faster and smaller in size. So this is another process where you take the model from the hub, run some other training process, and convert it. Okay, and now let's look at the production model. We cannot just run the model directly. In general, you also need to deploy the model into an application. So kind of this is the entire diagram for the ML framework, starting from datasets all the way to the application. It kind of looks similar to the salsa diagram, except it's a little bit expanded because we have all of these iterations and all of these loops. But we still have all of the risks that show up in traditional supply chain. So once the model is in storage, storage can be compromised. Or we can accidentally use the bad model into the application. Or the model can be poisoned, the dataset can be poisoned, and so on. And we can solve this by hashing models and datasets as soon as they get produced, assigning them, and then verifying them at each step. So for dataset, at each step of the iteration, you hash them once the dataset is ready. You verify it before it gets used. For models, once it's trained, you hash it, and you keep verifying each time you deploy it to storage or you deploy it to the application or you use it for the next iteration. So that's the ideal goal that we hope to reach into, let's say, 2 to 3 years maybe, or maybe earlier. What we have so far is this part. We want to make sure that once the model is trained, any modification that happens to the model before the model gets put into the production, into the application, gets detected. And we do this via SigStore. So basically, we implement a mechanism to sign the models and verify the signatures using SigStore. And how does this work? Let's start in the middle box. As the model trainer, the ML framework that you use, the pipeline that you use to train the model, will connect to the SigStore certificate authority to get an identity token and a certificate. That certificate will then be used to sign the model, and you put everything into the SigStore transparency log, and you get back the log inclusion proof, which you can attach with the certificate and the model and upload this to the model hub. And at this point, the model hub can verify the signature, can display a verified badge on the model card. So now users that go to that model hub will see, okay, this model has been verified. I can verify the signature myself if I want to, or I can trust the model hub, and I just download the model from there. Now, the users can serve the signed model. You can verify the model signature also as the user. So if the storage that you use for your application can support multiple users writing the model there, you can also do verification at that point. Okay, why is the model signing so hard? Because in general, you think signing is, I have an artifact on disk. I just hash it and then sign the hash. The big problem is that models are huge, from hundreds of gigabytes to terabytes for LLMs. And because they are huge, if the model is already on disk and you try to hash it, it's going to take a long time. So as an example, 1 terabyte model takes around 900 seconds to hash. And you don't want to spend all of this time each time you train a model. It becomes especially important because during training, you keep saving checkpoints from every few rounds to every few rounds of training because the training job is expensive and runs for a long time. You don't want to have to reach a situation where one machine during the training process dies and you have to restart the entire training from the beginning. So instead you keep saving checkpoints, and if something happens during training, you restart from the previous checkpoint. But now this opens the opportunity for an attacker to modify a checkpoint that you just saved and then kill the job such that now you start training from an altered checkpoint. So you'd basically need to hash every checkpoint. But now if you hash every checkpoint, each time you run the training, you have to delay training by hashing the checkpoint each time it gets. And not all of the checkpoints are useful in production. In the end, you only care about the final model. So you always have the contradiction between I need to hash a lot of things that will delay my training job, but only one will be useful after the training job completes. And there is another issue with the checkpoints. In general, a model contains the weights, but the checkpoints also contains the optimizer states, so all the gradients. So in general, the size of a checkpoint is double the size of a model. So you actually spend even more time to sign a checkpoint. And the checkpoint and the final model in general are different formats. So even if you say, I signed the checkpoint, I hashed the checkpoint, now I want to convert the final checkpoint to a model, you have to rehash it again because they use different formats, and you cannot just say, I take the weights from here and put them there and I'm done. So you still have to hash a lot. Okay, and other issues occur after training. In general, when you train a model, you generate the weights for one specific format, and then you keep converting it for others. So for example, let's say I train a model with TensorFlow. I save it as a TensorFlow model, but now I want users to be able to use this model with Apple Core ML or with PyTorch. I can run a simple converter that reads the weights into memory and saves them into another format and put everything together into a single place into the model hub. So in model hub, into a model hub, or like in Hugging Face or in Kaggle, when you go and look for a model, you would see, let's say, Llama 2, but in there you would see that you have files for TensorFlow, files for PyTorch, and so on. As the user, I only care about the model that I use for my framework. So if I download a model from Hugging Face with Keras, I only care about the files that are needed for the Keras framework. I don't care about the other ones. So now when I verify the hash of that model, I only care about those files. And then, of course, there is the issue that both training and inference for a very large model is run in a distributed fashion. So you would want each distributed host to hash only the parts that it touches, instead of having a central authority hash everything and delay saving or training. So what we have so far is a hashing library, which is divided into 3 layers. So starting from the bottom going up, we have a hashing layer where you specified what hashing algorithm you want to do for a model and at what granularity. So you can hash a file of the model, or you can hash a tensor or a tensor slice, depending on how the distributed training goes. Then the next layer is the serialization layer, where basically you are taking the model from disk or during the training process and you are hashing it. You are computing the digest. And then finally, the signing and verification layer, where we call SigStore, we get the signature back. And what we're working now on is to create a public API on top, such that in general, users would just have model.sign, and in the background, it will do whatever is needed. And if the users need customization, they can pass additional parameters to the public API. And let's do a demo. So instead of training a model here, I downloaded a model from Hugging Face, because training it will take a longer time. And we can see that the model has 3 gigabytes. And now let's start using it. So I did some imports, and I saved some paths for the model and for the signature, so I don't have to type them all the time in the notebook. So now, as I said, the API has 3 layers. So the first layer is the hashing layer, where in this case, I'm using SHA-256 to hash a model file by file. So it's a file hasher and SHA-256. And this is fast because this is just defining a function. And then the next layer is the serialization, where I take the model with the hasher that I defined before, and I serialize it to a manifest. Basically, the manifest is the representation of the model hashes for every file paired with its own hash. Because I use the file hasher. This is the part that takes the longest amount of time, because this is the part that actually needs to look over the model bytes. So every model bit needs to be hashed at this point. And it should take around 16 to 20 seconds. I think it's finished. Okay, and now the next part is the signing part, where I actually take the manifest that I have before, I convert it to an in toto statement, such that I can sign it with SigStore, with DC. And this will run the SigStore authentication flow. So let me do that. I will connect with Google, copy this token, go back here and paste it. Okay, so at this point, the model is signed. And we can verify the signature. So now let's put on the model hub hat, the model hat owner hub. And actually, first we can check what the signature looks like. So it's a JSON file. It's a SigStore bundle that contains in it, it contains the inclusion proof. So you can also verify this offline. And in the payload, where is my mouse? Okay. In the payload, we have the signature, and the payload itself is another base64 encoded string, which we can decrypt. We can look into, and we'll see the manifest from the model. So in this case, because we hashed every model by file, we see that every file in our model directory, so for example, this Rust model, contains its own hash. And if I want to use the model from the Rust ML framework, this is the only hash I will need to verify. I don't need to verify, let's say, if I scroll a little bit down, here I have a tokenizer JSON, which is more useful if I want to use this model for fine-tuning. If I don't use it for fine-tuning, I don't need to verify this hash. Or here on top, I have a TF model H5, which is the hash for the model in the format used by a format you can save the model in for TensorFlow, and so on. So I don't need to verify all these hashes, only the ones that I need. And now let's actually do verification. Because in this notebook, I don't specify what verification pattern I want to use, what framework I want to use, I'm going to verify the full manifest. But in general, we can verify only a subset of it. So the first part is to read the signature and verify with the SigStore Python verify API. And this will just verify the envelope. So it'll verify that the model has been trained by me, with my identity, and the YDC issuer is Google. And then once I verify the envelope, then I can look into I can serialize the model that I have on disk and compare the two manifests, the one that comes from the signature, the expected hashes, with the one that I get when I serialize what model I have, which in this case, oh, I already ran it, okay. In this case, this should still pass because I didn't change the model. It's exactly the same model that I just signed. But what I can do is so in this case, the signature is valid. What I can do is let's simulate that I'm now an attacker. So the model is in storage, and I can delete a file. I can delete it from here, or I can actually go here, go into the model, and let's say I'm going to rename this one to something else. And now let's go back. So I basically, having access to the storage, I can change the model. And now when I go back to the model user, when I want to verify, this time, the envelope checking part will still pass because it's still signed by me and with the Google YDC issuer. But now when I want to check the manifest with the serialization from disk, this time this will fail because the model has been changed. And it will take a little bit more. Okay, so this time is invalid because the model has been changed. What other examples I have here, I can try to hash the model directly with SHA-256 SAM. Because this model is 3 gigabytes, the difference is not that big. So hashing with the library was 16 to 20 seconds, whereas this one is 24 to 30 seconds. So not that big, that's why we can still run it. But what is more interesting is the second part, where instead of hashing file by file, I split every file into the model into chunks, into shards of equal size. In this case, it's going to be by default 1 million bytes. And I hash every shard itself with Blake 2. So just to show that we can also have this part of the API. And again, I can serialize with a file shard serializer. And then when I sign this, I can sign it. Once that part finishes here in a few seconds, I can then sign it again with Sigstore. And I'll have to do the same flow. Let's pick a different YDC issuer this time. And we can still inspect the signature and the payload. So if I look at the payload now, this is going to be a little bit longer because now every file is split into 1 million bytes boundaries, and I have some files that are longer than that, so files will show up multiple times. So you can see, for example, for this one, it starts from this offset, and it goes to this offset, and that is the corresponding hash. And then above it, I will have the previous chunk, and so on. So that's what it will show up in the manifest. So now when somebody wants to verify this model, they'll have to look at multiple files at multiple entries into the manifest, but still only those that correspond to the framework that they use. And the last step, let's assume I'm again the user, and this model has been signed by me with a Google identity. That's what the README says. But if I want to verify it, because this time I signed it with GitHub instead of Google, this should fail. And indeed it fails. So this time the envelope itself failed. Okay, let's go back. What we have to do next is to integrate this with ML frameworks such that you could say, when you write the code to train the model, at the end you just say model.save, and behind the scene this would also sign the model directly. So an ML practitioner doesn't have to write additional code for signing. And we also want to integrate with model hubs such that you can upload the model to the model hub, and the model hub would immediately verify the signature on upload. Or if you didn't sign the model hub will offer you the option to sign the model there, which would entail to make the model hubs YDC providers, but this is doable. On the technical side, we also want to do some more performance improvements to make hashing even faster, as fast as we can. We want to support incremental updates to the manifest. So let's say I have a model that I already hashed, and then I decide, let me change something in the license file for the model. Or let me add another model format for, I don't know, let's pick another framework. Let's pick ONNX. I don't need to rehash the entire directory. I only need to update the manifest with the files that I modified or that I added. That's what should be ideal. And then we want to support streaming hashing. So instead of having to wait for the model to be written on disk and then hash it, we want to hash as soon as the bytes gets written to disk. And finally, what we can do, the next step is once we have the model signature, we can use the same hashing scheme for salsa statements, or we can add additional metadata to the statement that we have about the model signature. So we can say like, this model has been evaluated on this framework, and this was the score that got obtained, and so on. All of this can be also made transparently and secured by a signature, so it can be tamper-proof. And I will end with 4 QR codes. The first one is the repository where we have all of this. The second one is AI supply chain white paper that we published at the beginning of this year that contains a little bit talk on this and a little bit going more forwards on Salsa and maybe Guac for AI. Then the third one is the OpenSSF AI working group. If you are interested in this area, you can please join. And the fourth one is an invite to SixTorCon, where we can give a talk about how we can use Guac to understand the AI supply chain. So if you remember that long diagram here, we can try to use Guac to understand all of this chain from the end of a model to whatever iterations we had on the datasets. And I'll go back to the QR codes. And thank you. Questions?
I just had a question. When model is trained based on input coming from the other model, so you have a chain of model provenance, how have you thought about that?
Yeah, so if the model is trained from the the output of another model, instead of directly take the model and use it to adapt the new one, you can view of that as in this layer here where I have the data set. I don't see my mouse, but in the layer where I have the data set, that data set could also be the output of a model. So the loop that goes from data set to data set, that could be a model that starts from a data set and generates a new set of outputs that then can be used for training later. And we want to capture that in the provenance too.
Thanks for the talk. My question is about sort of the end-to-end guarantees also relates to the sort of scenario that you explained at the beginning. As a user, I'm wondering, so unless I'm able to sort of redo the entire training pipeline, what kind of guarantee do I actually get from the solutions that you've presented now?
So right now, the only guarantee that you get is that the model that got trained is exactly the model that you used into the application. So you verify the envelope and you verify the hash of the model. What we plan to do into the future is at the end of the training, in general, before you put the model into application, you run some evaluation. You test it on some test data set, on some test samples of what the user might submit to your application. That one could also be, you could also record the score on that evaluation into the signature, into the manifest, into the payload. And this way you cannot tamper with that. So now when the application user, so I forgot to say that on this diagram you see there are 4 colors. The dataset user is the dataset, the person that trains the dataset is not the same as the person that builds the application. That's why there are different colors. So the person that builds the application only cares to see that the model that they involve into the application is suitable for the application. So it has passed the evaluation tests with a high enough score. If somebody malicious can modify those scores to fake them, then the application will misbehave. But if those scores cannot be tampered with, they are included into the signed part, then now the application developer is more certain that they are using the right model for the application. And the same going back to the datasets. If the way the dataset got trained and what is the origin of the dataset and what tooling you have used to clean the dataset and so on is included into the signature for that part, and you can inspect the full chain of signatures all the way back, all the full chain of provenances all the way back, you can be more secure, you can be more certain that the model that you are using for your application is the one that you care about.
Thanks.
I'm curious what you get from the transparency log in particular of this system. I take it you can monitor the transparency log and find all models that are associated with your name. Are there any other claims that can be verified or can be verified by a third party?
I think right now that's the only one that we can offer. So you can see what models have been trained on your name or what models this entity has trained, which can be useful. So if you detect a malicious model on a hub and it is still signed by an entity, you can detect all the other models that that entity has trained and decide to lower the trust on that, or maybe detect like this entity got stolen, this identity got stolen. But in the future, we might want, for example, to push the entire evaluation of a model to a transparency log. So we evaluate the model, and the score would show up into the evaluation log, and you can see now this model has been evaluated on, let's say, a public dataset and a public Wikipedia dataset at this date. And then later, when it gets evaluated on the Wikipedia dataset at another date, there will be another entry into the transparency log, and now you can inspect, is the change in the score because of Wikipedia changed in between, or because the model was not suitable enough and some randomness just made the first score be bigger than the second.
Okay, looks like we've got all the questions, so thank you very much, Mihai. Okay, we'll now stop for the morning break, and then we will resume at 2:45. We have a talk on key transparency, and then into the lightning talk session. So we'll see you back at 2:45. So first up, we are going to have our final full talk for the day. And after that, we are going to jump into our very exciting lightning talks. So if you are a lightning talk speaker, please make your way to the front of the seat so we can have some easy and quick handovers. Lightning talks will be 5 to 7 minutes each. And yeah, we won't be taking questions during the lightning talks. Just enjoy the pace of lots of different topics coming at you and opportunity to follow up with folks at lunch. But
would it be possible to see the slides here as well?
perfect.
Remember to switch buttons.
Okay.
Did I put them? You have.
Oh, yeah, I'll give you this one. I just did that. Okay. All right, we're all set. Okay, so it's my pleasure to have a talk on key transparency today. And please welcome Daniel.
Thanks a lot. So I'm going to be talking about key transparency at Proton and specifically in Proton Mail. So I will. So I sort of assume that a lot of people in the room already know what key transparency is and sort of how end-to-end encryption works and so on. But I'll very quickly go through the problem statement and just to make sure that everyone is on the same page. And for the people watching online, perhaps that are maybe not as familiar, I'll sort of very briefly go through. How does our encryption work? Is basically when you send an email or also when you share a folder or file in Proton Drive or when you share an event in Proton Calendar, you look up the public key from Proton server and encrypt the message or the file or whatever it is with the public key and send it to them, and then they can decrypt it, which is great. However, there is a problem, which is that if the server wants to do a man-in-the-middle attack, it can give you a different key. And then if you encrypt it with that key, then the server can read it or the wrong person can read it. And in fact, it's really difficult to detect this because the server could re-encrypt the message with the actual key of the recipient, and the recipient would be none the wiser and the sender would be none the wiser. So it's actually fairly difficult to prevent this attack. So until now, the way that or the solution that we've had in place to prevent this is something that we call key pinning. So you can trust a specific key. For example, after you manually verify the key by, let's say, calling up your friend and saying, "Hey, I'm seeing this key with fingerprint DBD12 and so on. Is that indeed your key?" And then they say yes, and then you click, trust the key. And then after that, if the key ever changes, we'll warn you, and you can call them up again. But of course, this is a very manual process, and most people won't do this. Although a while back, when I looked up some statistics for internal messages, the number of internal recipients that used key pinning was actually around 30%, which is a lot higher than I had expected, but it's still obviously a lot lower than 100%, and we would like to protect 100% of our users. So that's basically, that's where key transparency comes in. It's basically intended to be a much more automatic a way to protect users against this attack. So the very high-level protocol, or very high-level idea, is that we publish all keys for every ProtonMail address, and then every user. So we publish it to a transparency log, and then every user will go and check their own keys in this transparency log and check that they match their own keys. And then when sending a message or a file, you also go and check the keys that you receive from Proton's key servers against this transparency log, and assuming that the recipient has checked their own keys, and assuming that you're seeing the same keys, given that it's in a public transparency log, you can know that they are the correct keys for that email address, and that you're encrypting hopefully with the right keys. And it's important to note that this gives you a slightly different guarantee than key pinning, in the sense that you only know that the keys are the correct keys for that email address, at the point, as long as the sender is, continuously verifying them and warning you if they ever change, because the owner of the key is the only person that can know whether they're correct. Whereas with key pinning, you're warned immediately if the key changes, and then you can, as I said, go and call them up. So this is a detection mechanism rather than a prevention mechanism. But nevertheless, that's sort of the trade-off with it being an automatic system that can protect everyone by default without having to do any manual action and without impacting the user experience. But nevertheless, it's it gives you a lot more security than doing nothing. And also, in my mind, it's sort of a deterrence mechanism as well, to hopefully dissuade the server from trying to do a man-in-the-middle attack in the first place, because it might be detected, right? So a brief history of, I keep forgetting to switch both. Brief history of the development of key transparency at Proton. We started in late 2018 with developing a version of key transparency based on Konix. Then we spent some time on it off and on. We didn't work on it continuously from 2018 till 2023, well, development happened. Took a while. It turned out, to be quite a large project. Also, since we developed our implementation from scratch, so was quite some work. Eventually, in 2023, early 23, Tore Goebel from ETH Zurich came in and did a project. Well, we did a project with them. And he brought in some ideas, particularly from the Seamless and Parakeet papers, and we adopted some of them. So that I would say improved the system a bit. And then late 2023, we launched in beta. It's still opt-in, even today, which I'll get to later. But you can use it. No worries. And earlier in this year, we published a white paper together with Tore Goebel, sort of describing how the whole system works. So I'll have a link at the end of this talking in case you want to have more details. So I'll go through each of the. I'll go through each of the 3 steps briefly to each of the steps that I highlighted in the high-level protocol and dive into a little bit more detail to see how they work. So first of all, for publishing the keys, what we do is every 4 hours we publish what we call an epoch, which is basically a Merkle tree of all the keys, the history included, of all the keys of every email address at Proton. I'll show the structure in the next slide. Yeah, and then we compute the root hash of the Merkle tree and the chain hash, meaning the hash of the root tree and the previous root tree, so that we include the entire history. And then we request a TLS certificate for the chain hash under some domain. Of course, we've already had quite some interesting discussion about the use of certificate transparency to bootstrap our trust here at this summit, and probably there's better things we could do in the future. But for now, this is the way that we bootstrap our trust in key transparency, is by piggybacking on certificate transparency. So basically, the certificate with the chain hash gets published in certificate transparency logs, and auditors can go and check that we've only published one chain hash for a given epoch. So here is the structure. Well, here is the structure of the tree. So basically, we have a tree of 256 levels. The path of the first 256 minus 32, the top layers are determined by a VRF of the email address, and then the lowest 32 levels are determined by the revision. So we have a single tree for all the versions of all the keys of everyone. For historical reasons, we start at revision 1 instead of 0. So revision 0 at the very bottom left is always empty, which we is sort of a historical accident, but we can we could at some point we could use it to do something special there. But for now, it's always empty. So at revision 1, you have the sort of the first version of the set of keys for that email address, and then at the next revision you have either the next version, or in this example you might have what we call an obsolescence token, which is just a token saying this email address has been disabled, for example. So then the auditors, we rely quite heavily on external auditors in our key transparency scheme. So they have to check a couple different things. First of all, as I said before, they have to check that there's only one root hash or chain hash per epoch ID in the certificate transparency logs, because otherwise we could show two different trees to different people at the same moment. Then they have to check that all the epochs form a consistent chain, and they have to check that the subtrees, meaning the lower portion of this tree, are append only with an asterisk, meaning that for stale entries, which are revisions that have been unused for more than 3 months, they can be removed. Epochs that are older than 3 months currently cannot be verified anymore anyway, because the certificate from Let's Encrypt will have expired, even though in the future that might change. But I think having some mechanism to purge old entries is also useful. So then we go to the next part of the protocol, which is once we've published all these keys, every user of Proton will have to verify that their own keys matches what we have published. So the procedure is basically you have to regularly fetch the latest epoch and verify the certificate that has been requested for this epoch, and check that the fingerprints of your key in the latest revision match your own private keys. And the private keys, we encrypt them with your own password. So assuming that only you know your own password, you can know that they're your keys, and therefore you can check that the correct keys have been published. Then you also have to check that any previous modifications that you made to your keys are included. So whenever you create a new key or you mark a key as obsolete or whatever, we create a local artifact that we call a signed key list that you basically store locally that says, well, I've updated my keys, so I'm going to check later that they were actually included in the key transparency log. And we have a maximum merge delay similar to certificate transparency, although in our case for now it's 72 hours because we don't like to be waking up on the weekend. But we hope to one day, bring it down as we're more confident in the stability of our log. Then you also have to check that additional changes that were not made locally are properly signed and are correct. Because in our system, you may have multiple devices, so you can change your keys on any of those devices. And that's again where the signed key list comes in. I'll actually think I have a slide about that. So yeah, this is what the signed key list looks like. It's basically a signature plus the data, which says, here's the list of keys. Each of them will have a set of fingerprints, which are like the OpenPGP subkeys fingerprints, which are hashed using SHA-256, and then they say, well, whether the key is primary or not, and the flags, which are like, is this key obsolete or not, for example. And this data structure is created every time you make any change to your keys, and is stored also on the server, and then when you log in on a different client, you can check that the change that has been made to your keys is correct, as long as the primary key, which is the first key in this list, is still included in the new change. So if you have like a clean break, let's say you forget your password and you reset your password and you generate an entirely new set of keys, then obviously the new signed key list will be signed by a different key, and you actually can't check that the previous revisions in the key transparency log are actually correct, because you don't have the key to verify them anymore. And in that case, we have to warn the user. But hopefully they will know that indeed they had reset their password, and that that is expected. If they hadn't done that, then that might indicate some kind of attack, right? So then here are some screenshots of the what we call the self-audit, but perhaps more aptly named self-monitoring in Filippo's parlance. So here's the UI. So first of all, yeah, we have a setting to enable key transparency, and once you do that, you get an option in the settings drop-down that you can go and look at, and see that indeed your own keys have been correctly verified in the key transparency log. And you can see a list here of the addresses that has been checked for, and that's actually relevant for security in our case, because you might have multiple email addresses in your account, and whenever you log in, the server actually tells you what those email addresses are that you have, and if the server were to hide one, then the self-audit or the self-monitoring wouldn't run for that address, and then you might miss some malicious changes to the keys for that address in the key transparency log. So for now you have to check that the self-audit was done for the correct addresses. We have an idea to fix that by having a signed address list that basically authenticates what your list of addresses is whenever you make a change, or when one of your addresses gets disabled, for example, you would get a warning saying, sorry, this address has been disabled, and therefore we can't audit your keys for that address anymore. And that also means that you would have to go and warn your contacts, for example, that if they send email to that email address, it's no longer necessarily secure, right? Because all of this entire key transparency model only protects you as long as you own the email address and you're able to audit the keys for that address, right? As soon as the ownership changes, then a different account is in control of those keys, and then it's expected that those keys will change. So if something fails, then the user interface will look like this. You'll get an error dot and a warning or an error in the dialog saying something went wrong with verifying these keys, and then you will have to perhaps go on Reddit to complain, saying that well, hey, maybe Proton is trying to attack me, or perhaps there's a bug. Probably the latter is more likely, but yeah, eventually we'll have to get rid of all of those bugs to make sure this never happens, but we're not quite there yet, which is why it's still opt-in. So then for the third part, is verifying the public keys of other users when you send them an email. And there, the user interface looks like this. Well, basically what you have to do is you just fetch the keys from the key server as normal, and you fetch the latest epoch and verify the certificate again, and check that the epoch includes the public keys that you got in the latest revision. And when it happens, you get a nice blue lock. If that doesn't happen, you get an error. So here we're aiming for having no indication in the positive case and having a negative indication, in the error case, rather than requiring the user to look for and check for some kind of positive indication, like a check mark. Also because we already have a check mark for binned keys, so we didn't want to have two different indications or two different check marks that the user would have to look for, right? So there is an edge case here, which is if the recipient keys recently changed. You might remember that I said at the beginning that we issue an epoch every 4 hours, which is quite a long time. And during that time, the keys might change. And in that case, you get the signed key list that user created and store it locally as well. We still accept the keys and we still show a blue lock. But in the next periodic audit, so this is like at the same time as you're doing the self audit or the self monitoring, you also check the signed key lists that you got for other users and check that they indeed were included in the next epoch, or at least within an epoch in the next 72 hours. And if that doesn't happen, you again get an error in the same place as the self audit error, saying that you got a key for some address that actually was not the one that ended up being included in key transparency within 72 hours. And it tells you to, go and check the keys. Although there is an interesting, UX problem here, which is that if you actually go and check the keys, at that point, they might actually be correct because the server could serve you different things at different times. So actually, the only thing this error really tells you is that at some point in the past, you got some wrong keys, and we have the fingerprint of those wrong keys, but we don't have the keys. So it's actually still a little bit of a UX challenge, I would say, to perhaps more clearly explain to the user what might have gone wrong, especially since we don't really know what went wrong, right? We just know that something went wrong, and either the server might have been malicious, or there might have been a bug. Again, we would like to get rid of those bugs, but we're not quite there yet. So there are a few other interesting edge cases. Yes, good, thank you. One is around deleted and transferred accounts. Here is a screenshot, a redacted screenshot I got in a bug report from our CEO, Andy, who said, here's an email I got and I see a warning. And the warning is, the warning was because the account had been deleted, and so we could no longer verify the keys and verify the signature. So we ended up saying that, as I was alluding to before, key transparency can only protect you as long as the sender owns that email address, right? So nowadays we no longer show this warning, and basically, if someone no longer owns the email address, they basically have to tell you, don't send me email there anymore, because now that email address belongs to someone else, right? Then there's a whole bunch of other issues. I won't go through all of them, also for lack of time. Some of these are legitimate bugs. Some of them are just weird things in the web app. Stuff like type error, cannot create property 10 on number 9. That's not like that's not really explainable. Like the best theory I have is that there is a web extension doing something strange to our web app, causing us to, causing strange errors to be thrown. Others might be legitimate bugs that we still have to fix. But there's a whole bunch of false positives here that we still have to reduce before we can enable it by default. Then there is the white paper I was mentioning at the beginning. So here's a QR code. You can go and read the white paper if you want more details. And yeah, that's all I have. So yeah, thanks a lot.
Take a question. Any questions? Okay, no, thank you very much. Oh, sorry.
It's a small question. If anyone has anything more important, they can go ahead. But can you go back to the slide where you showed the user tree? Because I don't understand what it represents, because it seems like it's that one. It seems like the hash binary VRF thing is essentially another tree that's rooted as a leaf of the big tree, and I don't understand why it has so many empty leaves.
So conceptually speaking, the way that we think of it is a tree of a fixed size of 256. So like from top to bottom, you have 256 layers, but then a bunch of them are obviously empty. So we omit those and basically, include all zeros when you're, trying to hash those subtrees. So it's a sparse tree. The alternative way you can think of it is you have one tree here, and then indeed you have a subtree at this layer, or you could also put a list here, right? But sort of for simplicity, we think of it as a single tree, so we have a single structure. But there, this specific structure is not actually very important. There are many different ways that you could encode it or represent it, and I think there are mostly equivalent. There is one exception, which is that, for example, in Seamless and Parakeet, they put all the revisions at like different points in the large tree, whereas we put all the revisions together under the VRF of the email address, which is has advantages and disadvantages. One advantage is that it's very easy to find all the revisions. One disadvantage is that once you know the VRF of Alice, you can find out whenever she changes her keys, for example, which there are some small privacy implications there. Thank you.
We're out of time for questions, but I'd like to thank Daniel, and please give him a round of applause. Yeah, I'll bring them up.
Thank you.
All right, who's ready for some lightning talks? Very sad. Let's try again. Who's ready for some lightning talks? Hey. So much better. Okay, so the next, we have 6, maybe 7 speakers. As of Wednesday, they were not speaking at this conference, but they have very bravely put themselves forward for some lightning slots. And this is going to be either really great, bit of chaos, maybe all of the above. But I'd really like to thank everyone who stepped up and is going to do a talk. And really appreciate you going with the flow and sharing your expertise. Okay, give me one sec. Can anyone see my mouse? Okay, there it is. Okay, so how it's going to work, we will have 7 minutes for each talk. I'll be timing the speakers, so I'll let you know when you've got 2 minutes left, and then 1 minute, and then it's time, and then I'll probably start like standing over and coming over. So, the one exception, Rasmus' talk at the end is going to be a 2-minute talk. So like a to the point Ignite talk. So is this? Yeah. Are we good for that? Okay, let's get that moved over. Right, do you mind?
All right, thanks.
you need to download it.
Okay. Can you give me access to that? These are the slides.
Oh, I didn't send you a link to them.
Yeah, I don't have
Weird.
access.
Oh, it's I sent it the link to Tracy at Tracy
Oh,
Miranda.
yeah. Okay, let's download this. Here's 1 sec.
Yeah. Yeah, that makes sense. I don't know the interface. Okay, great.
Okay, so yeah, first up, let's give a very warm welcome to Frederick.
Thank you. Thanks. How do I navigate here? Hold on. Okay. Can I full screen that somehow? I forget the.
I promised you chaos. This is. And you can use that.
Yeah. Oh.
All right, take 2. Welcome, Frederick.
Nope, it's not working.
Oh,
I
there
can.
you go.
Oh, there we go. Okay, great. Hello. I'm going to talk about. I think maybe we should call it runtime transparency. I'm not sure. Yeah. All right. Let's go. My name is Fredrik Stromberg. I'm involved in these companies and projects. And one of the projects I'm involved in is system transparency, which I made up because I wanted to prove to an extent what we're running on our servers. It turns out you can't prove it, but you can, give claims about it. And I call it system transparency. Hal Finney called it transparent server back in 2001. Keylime is sort of similar to it. Project Oak is also sort of similar to it. Apple Private Cloud Compute, which was launched earlier this year, in their excellent blog post, which I think you should all read, or I can highly recommend it at least. They talk about verifiable transparency and runtime transparency. And given that system transparency has been a project for 6 years now, and it's tied to how we want to implement it, I thought perhaps there should be a vendor-neutral term which should not be system transparency, or Apple Private Cloud Compute for that matter. And I propose perhaps runtime transparency. So what is... I'm going to talk about how I think about this concept and in what ways it's general. So the way I think about it is we have transparent systems, or we want transparent systems, and the fundamentals are hardware, software, identity, and behavior. More fundamentally, it begs the question, what must I trust? Or rather, what must I be vulnerable to? Because trust is about vulnerability. And I think we need to be, we pretty much have to be vulnerable to the hardware and the operator who provisioned it. I know maybe you don't need to in some cases, but bear with me. So you have the hardware and the individual who touched the hardware. You have the software and the individual or individuals who touched the source code. That's what we have to be vulnerable to. Which begs the question, how do we construct an authentication mechanism for these things we must be vulnerable to? Clearly, there should be at least 4 keys here, right? One for the hardware, one identity for the hardware, one for the software, one for the operator, one for the developer. And we want to tie these 4 things to the behavior of the running system. And that's what the system transparency authentication mechanism will try to provide. It will try to provide accountability for running systems. And if we think about authentication mechanisms more generally, what is it? Well, we have some type of authentication that is done by establishing trust in a certificate. The certificate contains an identity and a public key. and the authenticated key is used to establish secure communication using ECDH or something like that. And that's TLS. So we have identity, like domain name, human readable identity. Then we have cryptographic identity, the public key. But if we look at remote attestation authentication mechanisms, they tie human readable identity, cryptographic identity, and other claims about the remote system to a public key that we then use to establish secure communication. So we authenticate this public key or this ECDH handshake, and we can use this authentication both to authenticate a secure communication connection with WireGuard or TLS or whatever, or we can use this to authenticate the public key that we use to sign things, like files. So let's go back to the fundamentals. Computers have a physical reality, and that reality is hardware. If we zoom in on that. Actually, I'm not going to do that. I don't have time to talk about hardware. Okay, so we can model this. We can model hardware plus software leads to behavior as a 2x4 matrix where we have a few phases. And we think about them implicitly, but I've tried to make them explicit. So we have the human readable phase of the software, which is the source code. We have the in-brain process of your conceptual understanding of the source code, including your mistaken assumptions about the behavior of the program, because whoever wrote it was writing spaghetti code. And then we have the hardware. The human readable version of the hardware is the blueprint or the Verilog. And then we compile the source code, or we synthesize the Verilog into a physical construction, or a PCB in the case of hardware, or a build artifact in the case of software. But what we do, where we place our trust, is actually in the the running system's reachable state space. So if you have a piece of hardware that only needs to do one small set of behaviors, you could implement it all in Verilog. That's great. But if you don't have the money to make your own chips, one for MS Word, another for Apache web server, a third one for your WireGuard VPN relay, and so on and so forth, you need programmable hardware, which means that you have on a 32-bit system with 1 gig of RAM, you have more possible states than there are elementary particles in the universe. Thus, the purpose of software is to converge the running system's reachable state space on the small set of behaviors that you care about, and not the ones that the attacker cares about. And we do this by connecting these phases using various technologies, which I don't have time to talk about in detail, but essentially what we need is to use secure network communication protocols and their authentication mechanisms. We take inspiration from those. We combine that with remote attestation and reproducible builds and transparency logging with distributed trust assumptions, and boom, we have a remote transparent systems. There's also some underlying philosophy, which I don't have much time to go into, but essentially my point is that there are two complexities that matter here. The first one is amazing. The only quantifiable security margin technology we have is cryptography, because we can formulate it in terms of how many exajoules of energy, how many Dyson spheres, how many tons of computronium, and how many millennia do I need to crack one instance of AES. And then there's the conceptual complexity, which will continue to rise, and as complexity continues to rise, the expected behavior of the system and the actual unintended and surprising behavior of the system will diverge. The delta between them is attack surface, and our job is to figure out how do we keep them together. And my short list is this, which I'm happy to talk more about some other time because I'm out of time. Thank you so much.
Fantastic. That was really great. Thank you so much. Okay, yes, please get connected. I'll take my laptop away. No, that was a really strong start. Let's give Frederick another round of applause. That's good. Okay, so from runtime transparency, we're going to go more into the open source world.
Yeah.
And please welcome Yogesh.
Welcome, everyone. Good morning. Thank you for inviting me for a lovely talk here. So I'm going to talk about the exciting project we are having known as Project Verizon. So setting the scene, I mean, why do we need this? What it is all about? So many times in the industry, you have scenarios where a relying party or a user wants to ascertain a machine's identity, or whether the environment on which the machine is running or the firmware or software the machine is running is trustworthy or not. And that's where we go to the world of, and what are the use cases where we need it? Like, when let's say the device is connected to the relying party or to the network, the relying party wants to know whether the device is running trustworthy environment or not, or whether it is in the right state before I can talk to that. Let's like a banking system wants to communicate to the user, or the user wants to communicate to the banking system, or similarly, like releasing valuable resources like a ML model needs to be deployed for inferencing or for training, then whether the environment is in the right state before I can deploy the model. So there are multiple use cases like that. So that's why we call attestation, just to inform that this is not the salsa attestation, but this is remote attestation. But I don't use the word remote because it can be used in local environment as well. So it's just called attestation. It's just to prove that the environment is trustworthy, whether it's trusted execution environment or some other type of environment. For that, to prove that, the entity produces a signed evidence, which is known as attestation report. But attestation report production is simply not sufficient because one has to verify the report, and that's where the verification has a huge role and a huge importance in the industry. And that's where attestation verification comes into picture. But there are certain challenges when building such an attestation verification service, because based on different deployment, different use cases, different type of hardware, different type of technologies, you have multiple types of attestation verification services, which means harmonizing this industry is a challenge. So because you need different type of business relationships, and verifier then becomes customs to individual use cases or individual type of hardware. That's why we went with a solution which is building common components or set of tools or libraries which one can quickly assemble to build an attestation verification service catering to their deployment. So that's why we started the project, open source project called Verizon, and I'm going to talk a bit about it. It's Verizon stands for Verification of Attestation. It's fully open source and open governance, and it has the tools and libraries you can quickly take on to build an attestation verification service. And it's a community participation from multiple organizations, and we have reference Docker deployment, and cloud work is ongoing to deploy instance in cloud. So that's how typically you would see in one of the particular deployment where the manufacturer deploys a device in the field, and when a relying party or an application in the cloud wants to bring the device on board, it would ask the verifier service to check the trustworthiness of the deployment, or test the trustworthiness of the device before admitting the device into its cloud. So just going through this few of the design highlights. It's a very flexible deployment model where you could deploy the service in public, private, multi-cloud, single or multi-tenant, and potentially to deploy locally as well in a trust zone kind of environment. We fully embracing the standards in ITF, so it fully follows the RFC 9334 as well as TCG DICE endorsement. It's a fully policy-driven and extensible via plugin. That's why if you have your technology, you can bring in here. So this is what is typically a verification flow looks like. You have a provisioning pipeline and a verification pipeline, and the boxes on the top are different type of attestation technologies, which on the left are the ones we support, and on the right is the work in progress. So if you have another technology which needs remote attestation, feel free to reach out to us, and we would be happy to discuss and bring it on board. So why am I here? What brings me here in terms of connecting with transparency, which is the talk of the subject in this forum. So remote attestation can augment the value of transparency by doing attestation of the root of trust on which the transparency systems run, especially like you run a transparency log on a hardware platform or in an environment. So you can attest the transparency, attest the application, or attest the full transparency log. And in addition to that, you can attest, like we saw USB Armory stuff being explained yesterday, witness running in a TEE. One would like to know the witness is running in the right environment, so you can attest the trusted execution environment as well. And then I will just make another interesting scenario where you can, Transparency can augment remote attestation, like an endpoint attester is, and there's a relying party and an attestation verifier like Verizon. So the attestation evidence is usually terse, so you can reduce only limited information from this evidence to run the attestation verification. But at this time, at the time of verification, a transparency log can be queried to get much more richer information about the data. Like you can get information about SBOMs or what this endpoint has gotten, what level of certification and stuff like that. And the richer data set can be given to the relying party so that it can make a decision whether to accept or to deny the endpoint in their network. So yeah, we would be very interested in taking feedback from you. And if you have any remote attestation use case, feel free to reach out to us. We'd be very happy to discuss about what is your use case, what you want to do, whether it is ML protection or AI security linking to platform security. So feel free to reach out to us. That's all I have. If you have any questions, feel free to reach out to me offline, or I'm happy to answer now as I have some time left, 30 seconds left. So. Thank you.
Thank you so much, Yogesh. Yeah, no, I really liked how you shared the project you're working on and connected it to what everyone in the audience has been talking about for the last few days. So let's give Yogesh a big round of applause. And finished with time to spare, so that's great. Okay, from there we are going to key transparency and a look at auditing key transparency. So we've got Thibaut from Cloudflare. Are you all set and ready?
You should be.
Okay.
The microphone is working. Perfect.
Great. All right. Take it away, Thibaut.
Okay. So we've talked a lot. We've talked about like key transparency during this session. There's been like breakout. There's been like various talks, even this morning, like with Daniel, for instance. And today I'm going to talk about like, okay, so like we have these logs which are logging like key transparency, like keys and like key changes, but who's actually like watching after them? And so today I hope to make a live demo from Transparency.dev Summit, so we can like actually check that some of these logs and the claim that they're making are actually valid. It will run out of my machine on like the Google network. Hopefully everything runs fine, but we will discover that in a few minutes. Before I start, I just want to check how many people have scanned QR codes on like Signal, WhatsApp, or etc. for their peers to check that it worked. Okay. Did you ever get a notification that like or the user phone, your contact, has been updated? Okay, so quite a lot of you. Did you keep on contacting these users? Okay, it was just like a side thing, but like I think what it highlights is like it's like very difficult in a like real environment practice to make like user experience right, because in the end you want to communicate. I think through that, like key transparency is like a very big commitment to like make sure that like users, even in the future, will be able to check that, and other people will be able to come audit and validate these claims. On that, key transparency, we've discussed like a couple of constructions, I think, of key transparency, and there's been a lot of papers. There's more than like what's on the slide. But what it means is like the design space is like quite broad, and like with like the evolution of deployments and like various companies and needs, there's been like kind of like a divergence in terms of like what has been implemented. So it mostly started with Connex, and then there's been like iteration. So like when WhatsApp came in, they've seen like the Seamless paper, which was some improvement over Connex. They updated it with Parakeet to like work at their scale. And like more recently, there's been Optic and Electra, which have not any known deployment to my understanding, but that's coming. However, like all these papers, we classify them as key transparency because they share mostly the same component. And so if we come to what was before key transparency, you had an application, you had like clients querying the application saying, hey, like I want the key for like this phone number, and you get the key. That's what's happening before key transparency. When you had key transparency, the application magically turned into a log. And so like you were querying the log, you could like have a proof from like the root of the Merkle tree to specific entities to like have some sort of proof that like the key that you're getting from the server is actually the one that you expect. There's still like some like split worldview problem. You still have like the log operation, and it's still like a commitment from the application owner that like they will try to make everything transparent so that you can verify it in the future. And so that's where what interests us today comes in, is like we want like an auditing. So I call that an auditor because like the auditor, there's been like witness mentioned before. In this case, the auditor is both witnessing that the log is doing some new operation. So for instance, like, I don't know, we have like every second we have a couple of keys which are updated. So we'll say every minute we will like batch this update, issue an epoch with like the number of updates we got. And so we need to make sure that like the new tree which has been constructed from this update is actually seen by everyone. So like that's what the witness would do. The witness would, I think Filippo explained it on like 2 days ago on Wednesday. The witness would like sign the hash of like the root hash of the tree and say, okay, like it has been seen at some point, and so like later down the line you can come and like validate it. The auditor does a bit more than that. It actually checks that like all the epochs are consecutive. It can also check that the epochs are unique. And it can also check, if we like a bit more complex system, it can also check that like all the tree transitions are valid. And this is like various claims that like one auditor can do. And it really depends on like what deployments you want to do. In the case of WhatsApp, for instance, WhatsApp publishes each of like the tree transition on an S3 bucket. And what Cloudflare does when it validates that the tree transition is valid, it goes to S3, pull it, copies the content, just in case we need to prove down the line that we've performed the verification properly, signs it, and like provides it to WhatsApp. Okay, so we provide it to WhatsApp. I say it's like deployed. Can we actually use it? Time to check. So a quick way to check it, we've made like just a small dashboard where you can see like the various logs that we audit. At the moment, we audit WhatsApp. So WhatsApp seems to be online, which is good. But this is like in an effort to like somehow like attempt to make things more accessible. But if you want to dive a bit more into the details, we've also like open sourced the auditing implementation. So it's all on GitHub. It's called Plexi because it's flexible. We've made it work with like all the logs implementation as well. And Plexi offers a CLI, which we're going to use now. So if I check my CLI, so first of all, I want to check what are the logs that Cloudflare is auditing. So I have like a remote URL, which is the URL of the auditor, which provides me like an HTTP API, which I could type by hand, but it's much more convenient to do it with a CLI. And so you can see at the moment there are 3 logs that we audit. We audit like a test namespace for ourselves, we audit a test namespace for WhatsApp, and we audit WhatsApp. Great. Now we want to like validate that Cloudflare has actually like produced a signature for like the latest WhatsApp epoch, and has also validated the proof. And we want to check the proof locally and see if like actually Cloudflare did a good job. So we just do Plexi audit. What Plexi audit will do is it will request the signature, what the epoch from the API, check the signature. It will download the epoch from S3, validate the epoch locally, and compare it to ensure that like it's actually like the good job that like Cloudflare has done. You have a bit more information, so like you can specify the cipher suite depending on like the log type you're using. You can like see like the epoch highs, digest, and etc. And that's it. If you have more question, I'm happy to answer, and I will be back to the slideshow with like a lot more links. That's it. One question?
Go on.
Hi. So yeah, this is great. Clearly, this is needed to like, close the loop. I'm curious. Like, doing this probably costs you a bunch of time and resources. What's the incentive for you?
No, I mean this is like definitely the right question. I think like there are a couple of incentive. We would like to make like end-to-end encrypted messaging more secure. For WhatsApp, WhatsApp has a deal with us. They pay us. At the same time, there's two phases, I think. Like in the slide before, I was showing like there's two phases. There's like the phase where you just only witness, and this is like very low cost, even though like making it sure it's available has some cost like inherent to like what we're running. The full auditing requires that like we understand the structure of the log so that we can like audit it. And it also depends, like if you're using Colnix, for instance, it might be harder for us because the constraints are bigger. With Pancras, it's simpler. So like we've also like make sure that like we understand the structure of the log. We have like some computation. So like this is more intensive. And then comes to like, why would WhatsApp pay us for actually doing that? And it comes down to if like in the first system, you already get value when you have a transparency log without having auditors. But having auditors that like are able to check, either provide a signature to like avoid some split view, or provide some additional guarantees that like your construction is valid, helps to protect your users. And so like this is a value that like WhatsApp sees through that. So there's different use cases, and these different use cases might end up having different type of like auditing / witnessing associated to them.
Okay, thank you very much.
Okay, I leave it to Bess.
Yeah, Patrick, we're not really doing questions, so I'm going to allow that because he was so brave to do a demo in an Ignite talk at last minute. But yeah, no, that was great. Thank you very much. Okay, next up we have Baz, who'll be tackling post-quantum. Do you have a microphone?
Yeah.
Okay, ready?
Okay, thank you.
Go.
So this is another breakout. I think this will be boring for a few of you, but I noticed that in none of the presentations there was an intro on post-quantum cryptography, but there is interest in it. So I thought I'd put together at least some slides to have some takeaways. And if that whets your appetite, I put some references at the end. Well, we all know that quantum computers are going to break cryptography. The big question is when. And people throw around, there's this new big quantum computer with so many qubits, which is like the size. But one thing you should realize is that quantum computers are analog machines, so it's not just about the number of qubits, but it's about how good they are. They have noise, so there's at least 2 dimensions. And if we're looking at, this is a summary in 2021 of the quantum computers. So on the bottom left, there's a gray area. With on the horizontal is the number of qubits, vertical is how good they are, the noise. And if this gray area grows and it hits one of the red lines, we're in trouble. So this is the year after, and this is the year after. So the gray area is growing, right? So we don't know. Will it keep growing at the same pace? Will it halt? We don't know. Also, notice that the green area, which came down. So if quantum algorithms get better, then also that can also happen, of course. So we don't know, but governments are worried. So the United States government wants to have the United States transitioned by 2035, which is not going to happen. But I mean, it's an ambition. And the CNSA2, that's the guideline of the NSA. They already require now, if you want to be CNSA2, you have to be PQ. So there's urgency. So another thing that's important is that the urgency is quite different between different types of cryptography. And so for TLS, you have key agreement and signatures. Key agreement is urgent because people can store encrypted stuff now and crack it later with a quantum computer. So you want to upgrade this as soon as possible. But signatures are less urgent, right? We only need to have this sorted once there is a quantum computer. At least in TLS, I mean, you have also long-running signatures in cars or firmware updates, but it depends on your application. Oh, another thing to notice is symmetric key cryptography. Some people say you need to double key lengths. That's absolutely not required. AES-128 and SHA-256 are completely fine. No need to change that. Okay, so key agreement, we are already deploying this. This is the number. This is the traffic, human traffic we see that's already using post-quantum key agreement, and that's now at 18%. And I expect this month it will probably go even higher to maybe a quarter. And before the end of the year, I think it might be even 30%. Who knows? It will go up. But that's key agreement, so that's nice. But signatures are the pain point here, and also you will feel that signatures are the pain point. And the reason is mostly they are big. So here's a big table, And as you can see, MLDSA, which is the workhorse, that's has a public key of 1.3 kilobytes and a signature of 2.4 kilobytes, which makes it a bit annoying if you want to have a lot of witness signatures in key transparency, for instance. You have Falcon FNDSA, which is smaller, but it uses floating point arithmetic in signing, so also not great. Hash-based signatures are not that great. Either they're also really big and slower to sign. There's also some signatures in an on-ramp, so there's a new competition. So these four, they're already standardized. There's a few bunch in the new competition. They all, well, a key sign looks nice in the sizes, but if you look at the CPU time, that's not really ideal. Then another interesting one is UOV, which has nice small signatures, 96 bytes, but public keys of 70 kilobytes. So it's maybe it fits your application, but it's going to be tricky. And this is only signatures and key agreement. If you ask questions about more fancy cryptography like OPRFs, no, you can ask Elena about post-quantum OPRFs, but they're not that great. Of the fancy cryptography, only a fully homomorphic encryption is already post-quantum, but for the rest, it's very, very difficult. Okay, that's what I wanted to give a web chat, but that's it. There's 2 links. Okay. Any questions? Or I think I'm over time.
Thank you so much for that lightning talk on post-quantum. Robin, do you want to?
It's actually too close.
Tough act to follow.
Great.
So, are we on?
Are you ready?
Yeah, I'm ready.
Go for it.
Cool. I'm Robin, and I'm mostly involved in. Are we going to. All the security? No. Why is that? Right. Okay, I think we're good. Right. So, I'm Robin. I work for Data Trails, and I'm mostly involved in our log implementation there. What do data trails do? We provide searchable, shareable, tamper-evident claims about data, and we try to make those transparent, of course. So this talk is going to zoom in on a tiny part of the log of the OWL that I think we all want to be as boring as possible, and why, in particular, what drove us to choose an MMR-based tile log. So we had a wish list. We wanted fast appends. We wanted the writes to the log to be coordination-free, and we wanted to be able to deploy new writers easily and take them down and horizontally scale them. We wanted easy replication of the logs once they were written so that this could lower the barrier for external auditors. If we want these logs to be checked, we want them in the hands of auditors and verifiers as easily and quickly as possible. We wanted good storage locality for generating the proofs of inclusion and consistency. So if you're coming along and you want to provide a receipt to a Skit consumer, or you want to just hit one place in the log, generate the inclusion proof, and hand it back to them as quickly as possible. If you're doing consistency checks across the log, you want to be able to handle that one piece at a time as quickly and easily as possible. I wanted to make friends in the operations team. I wanted to be able to give them a really simple story for how to retire data once it was end of life. We've got retention periods for all of our customers, and after that expires, their tail of the log is no longer interesting. We want them to be able to just chop it off at the end and not think about how that relates to future data. And for onboarding, we want to be able to have customers sign up and have the log just start up and start writing to it immediately without any fuss or fanfare. So those are the things that were on our wish list. And we picked Merkle Mountain Ranges. They crop out in a few places. They've got lots of names. Poster order traversal tree, history trees, binary numeral trees are just among a few. They're also used by a bunch of blockchains, which might get some hisses and boos in this audience, but that's where they are. Structurally, they're very similar to the leaf tiles in a T-log. It's just a regular Merkle tree, and the bottom of the T-log tiles are roughly the same shape. With a Merkle Mountain Range construction, you get a 1D layout instead of a 2-dimensional layout. If we wanted to, we could probably produce CT-compatible proofs from them for interoperability purposes. But we're not a certificate log, so we give ourselves a pretty much free hand for doing these things. There is a background paper that's possibly interesting for if you're interested in Merkle mountain ranges and some of the underpinnings, especially for how witnesses can be made efficient. This paper is interesting for that. This is the tree diagram with numbers on, and some bullet points about what we like about this particular tree type. So the inclusion proof for any item just gets longer. This is because the position of every element in the tree is constant as soon as it's added to the log. That has some handy properties. The checkpoints are just a signed peak list, and that gives us a thing where the inclusion proofs all terminate at the same MMR peak, and over time that peak changes quite slowly, and that means that we don't necessarily have to change the witnesses for people that are interested in holding them. And in some circumstances, it means we don't need the single tree head per leaf, which can be inconvenient in some places. So we have to stick that tree in storage, and we stick it in tiles. And the way we handle these tiles is to only ever have to handle at most 2 at a time. There's only ever 1 partial tile. And the way we chain them together is we collect at the beginning of each tile the ancestor peaks from the previous tree that commits the previous tree. And as we start the new tile, we always get rid of a few that we no longer need, pop one on the end that lets us join to the one that's just completed, and then we immediately start writing to the new tile. And that gives us, it's just really convenient to write a builder for that kind of log shape. So if that's, I could read out the bullets, but I'm not going to in the interest of time. So then I'm going to finish up by talking about standards and working code. So COSI receipts is a thing that's in draft status with the objective of being a registry for verifiable data formats encoded in COSI and CBOR. A guy called Ori Steele has made a Sunlight Tiles TypeScript implementation, and that's helpful because CT is the example in that draft which establishes the registry. I've made a TypeScript implementation based on tiles just to show how close it is at the level that you care, where you care about distributing tiles and log data. It's a pretty close fit. It's not far apart. Data Trails production logs use this as well. They're all implemented in Go. We have a tool called Veracity, affectionately in-house, that we use for replication. And if you're interested in checking our homework or willing to verify our logs for us, we would really like to talk to you. And that's it. If you've got an interest in getting into the details of this, come and catch me in the BOF session. Thank you all very much.
Great. Thank you very much, Robin. Oh no, it's done that thing again. How do we stop it? Okay, I'm going to plug something in, but come up and. You don't have any slides. We need to. Okay. Actually, I'll leave that on green. Okay. I'll give you the mic and leave you to it.
Yeah.
Right. Please welcome Niels.
Yeah. So this is a witness. It's obviously secure because it uses an HSM, and that's nice because it has a smaller attack surface and some resistance to physical tampering. And therefore, if someone breaks my server, the service will not be completely compromised. Except that's not the case if this is a signing oracle, because then if someone breaks in here, makes any co-signatures they like, and my witness is useless. So let's do something different. This is a nice little device made by our sister company, Teletis. It's a computer with a USB port, and it has a burnt-in device secret. And there's no secure boot. It happily runs anything provided by the host it's connected to. The thing is that the app doesn't get the unique device secret. It gets something like the hash of the unique device secret and the app itself, the executable that you load. So each app gets a different secret. The current version of this thing doesn't have any storage. seat would rely on the host to store stuff, and it couldn't be authenticated and the thing. But that would not be used for a witness because the host could do rollback of the state. But the next version is supposed to have storage, and assuming that storage have sufficient integrity, we can run the witness on this thing. The host will interact with the log and the Bastion host and stuff, and pass the checkpoint, the signature, consistency proof to this device. It can record the latest tree head seen for each log, and it will have space for plenty of logs, and then it will do the consistency checks and the log signature check on device, and only co-signature things that are consistent. And with that kind of thing, instead of the HSM, we do get this property that break of this internet server doesn't completely break the witness. And I think that's something that would be really cool to implement. Thanks.
Great, thank you very much. I'm liking the props and the whiteboarding here. Okay, that brings us to a final speaker who's going to do a even shorter. It's a Ignite, a 2-minute stint. Please welcome Rasmus. Do you need any setup?
No. All right, cool. Still Rasmus. And yeah, I have on my free time, I'm doing something for fun and not for profit, which is to tell people that they should be running CT monitors. So basically you have a domain name and you want to know what is happening with that certificate. And this worked great when I was an academic PhD student and I met people at conferences because they only have a single domain name. So I tell them they should sign up to monitor, they do it, they get an email every 60 days and they're like, oh, this is really cool. Then I graduated and I met some sysadministrators and I tried to do the same thing. And what they told me is, Rasmus, you're crazy. And I said, what do you mean? Why would I want to do that? Why would I want to monitor CT logs? And then I do the whole DigiNotar story. And I was like, you know, the CA can be compromised and, you know, they can impersonate you. And they say, oh, yeah, we care about that. But you're still crazy. And I said, well, I don't get it. And then they said, well, we have hundreds of domains. So if we do that, then we will be spammed. And we will not be able to distinguish between a misissued certificate and something that is just renewed. So they would get multiple emails every day and just not be able to tell what is good, what is bad. So then I went back to the drawing board and I started drawing 2 circles. Then I talked a bit to Filippo and we started trying to draw an owl. And then we came up with something we called silent CT. So basically a CT monitor that's supposed to be silent unless there's any misissued certificates for your domain. If you think this sounds interesting, we have a prototype for it, and it's available on git.glassclar.east/rgdd/silentct, and I believe Tracy is going to put the link somewhere. So it's a running prototype. You can just click play on it, basically, and it will do this. And yeah, if you want to know more, please come and talk to me, and I'll tell you a bit more about the setting. So that's it. Thank you.
Thank you very much, Rasmus. Perfect. All right, wasn't that amazing, everybody? Let's give them a big round of applause. Yeah, no, thank you so much for all being so brave, putting yourselves out there, doing all sorts of different things. We had demos, we had presentations, we had storytelling. Yeah, no, that was really awesome. And that is a nice way to bring us to the end. We are going to do a little closing session now. We know in the afternoon we have more discussion and we have the Birds of a Feather session for folks who want to get fingers on keyboard. But just to mark the end of the talk sessions and for folks who do have to take off, we're going to do a little wrap up and closing now. So bear with me. Has everyone enjoyed themselves these 3 days? Yes. Great. I'm seeing a lot of nods. Okay. To finish, we'll do a a few thank yous, and I'm going to invite someone to say a few words as well. But I'm going to try, inspired by all our lightning talk speakers, I'm going to try something new. Does anyone know what a Kahoot is? Yeah, have. All right, so it's my kind of signature ending to any summit I run, where we're going to do a Kahoot. Kahoot is really weird these days, so this may or may not work, so bear with me. Okay, how this works is this is an interactive quiz you can all take part in. So you go to that website, enter that PIN, and then we will, I don't want it to start so soon. All right, I'll see if we can pause that, but we do have prizes, so I do encourage you to get involved. The questions are going to be based on some of the talks we've seen. Whatever answer I say is the right answer is the final decision. No arguments will be entered into. And yeah, the more you're paying attention on the first day, the better you will do. Oh, look, we're getting an amazing set of folks in. That's great. Keep them coming. I think we could even do sound. Oh, yeah. We got music too. Okay, is anyone still trying to get in? We've got a whole bunch of folks there, 33. Okay. And Patrick, I'm going to get you up here later with the prizes. So just bring those out. Okay. Okay, I'm gonna, last call for anybody trying to get in. We've got 35, okay, we're waiting. 36, 37. That's good. I'm glad you folks all stuck around for Friday. It will be well worth your while. Okay, we're gonna, shall we wait, Yogesh? Okay, all right, we're going. Welcome to the quiz. Okay, first question. Let's see what this is. Yes. Okay, what does C2SB stand for? And this is a fastest finger wins. So which of those things does C2SB stand for? Okay, got 27. I think some people should be allowed to win. All right, 29 of you said it is the Community Cryptography Specification Progress. I don't know why this is an autoplay, so it's going to go really fast. Okay, true or false? When it comes to cryptography, SIGSTAM only supports SHA-256 and that one. All right, 9 seconds. And this is from Rasmus' talk earlier this week. All right, most of you knew that. That is true. It's very opinionated. And it sticks with those. Okay, who is Drop? I don't know who Drop is. Nice try. Okay, Tessa has some getting started examples. Which of these is not a current example in the repo? Try out these examples, folks. They're awesome. There's no such Kubernetes one. I like how 7 of you went for POSIX. No, there is actually a POSIX example. Oh, Hayden's coming in, as is Baz, but we don't know who Drop is. Okay, Sigsta has a number of different projects. Which one is represented by this logo? You got to know the logo and you got to know the projects. But, or just guess, because fast is good. Yes. the certificate authority. And not many people knew that. It's interesting. And Josie jumps into the lead. Oh. All right, a brief shout out for folks in the Sigstore community. Do join us at SigstoreCon. I'll be there along with Hayden, Colleen, and a bunch of others. So, okay, in the talk on digital identity, which of these was not covered? It's an extra tricky one. This was Idona's talk, so she's gonna get that one. No help from Idona. Yeah, most of you saw the one that was made up, which was the qualification transparency. How are we doing? Josie's holding on to that lead. All right, true or false? A witness can verify the contents of your log are legit. Inspired by Martin's Anteaters. That's false. It verifies the hashes. Okay, let's see if anyone can knock Josie off the top there. Okay, USB Armory meets its goals of reducing the attack surface of embedded system firmware by using which language framework? This is from Andrea's great talk on witnessing. Can't wait to see these answers. All right, I am so glad no one's hit JavaScript. You're all doing well. Okay, some folks are on streaks. Let's go. 9 out of 12. Which of these was not a breakout space at Transparency.dev Summit? Fastest finger. This one's all about speed, if you were around yesterday. That's amazing. Everyone got that one right. So, does that change anything at the top? Oh, no. Shavin is making a comeback with 3 in a row. Nice. Okay, what bird became iconic at Transparency.dev Summit 2024? As if you need reminding, but... Oh, 3 have gone for an eagle. Okay, how many questions? Okay, 2 more to change things. In the SCT auditing talk, which of these was not a state-of-the-art PIR? We're not going to make things easy for you folks. Good luck. And I don't know if... Ask Lena. Lena won't be your only help now. Yeah, unlike Frodo, which seems to be a hobbit, Baggins is not one, but the rest are. Oh, well done, Josie. Everyone else has been knocked off, but Josie's holding on. All right. For the Let's Encrypt Oak log, what is the typical daily bandwidth? And this is from Matthew's talk. And apologies if to any of the speakers if I have misrepresented your talk in any way, shape, or form. It was amazing, 10 terabytes, spiky data, but still, yeah, huge bandwidth. Okay, we have some winners. All right, I don't know why this is racing through, but we're going to figure out those winners were. Just give me a sec. You can bring them out. Where did this go? Okay. Okay, I'm just gonna go find the winner list because that disappeared pretty quickly. Did anyone catch the 3 winners? Oh no, Kahoot, you're so terrible these days. don't know. It normally saves them.
You have to do it again.
No. I will find these winners. All right. While I look for the winners, I'm going to call up. Okay, I know Josie was first. Who do we have? We had Matthew and Martin. Okay, great. All right. Is Martin allowed to?
I mean, is Josie allowed?
We're going to allow Josie. Okay, let's get Josie, Matthew, and Martin. Come on up, and we will check the rest of the list to see if we can get the other folks.
Do you want to give the first place to the biggest one?
To Josie. So Josie, we've got you some transparency blocks to build some transparency systems. And yeah, a little memento of London. So we're going to get you all to, let me get a photo of you.
Do you want me to take a photo?
Sure. Yeah. All right. Can Josie, we get you over the winner's podium?
Say transparency.
Awesome. Thank you very much. And if we can find the rest of that list, we might have some more. But yeah, I'm going to invite Bob Calloway to come and say a few words of closing. Please welcome Bob.
Thanks, Tracy. I'm glad that we were recording that, so now we have transparency for the results of the Kahoot as well. So I couldn't resist. So as Tracy said, my name is Bob Calloway. I run Google's open source security team, which includes our efforts around Trust Fabric, as well as Sigstore, Salsa, OSV, Deps.dev, and a slew of other projects as well. Our mission in this team is really to make the world and the internet more secure. I guess that resonates probably with everybody in the room. And so we spend a lot of time going into places where maybe the incentives don't necessarily exist for-profit entities to make changes. And so really trying to build systems and apply them at scale to, again, make not just Google, but the world a safer place. There's three things that kind of came to mind as I was reflecting on this week. They all have thank you in them. So first off, thank you for all coming. I think this is, sometimes you come to events like these and there's a few people that are engaged and a lot of people are on their laptops and their phones and they're not paying attention. The energy, I think this last 3 days was really, really good. And that's because all of you showed up, all of you were engaged, having good conversations. So thank you for coming and being so engaged. Second, you probably don't hear this all that often because if we do our jobs really, really well, nobody knows that our stuff is here. So thank you for what you do. It's a thankless work to be the plumber of the internet to underpin secure communication, whether it be TLS over the web, whether it be communication over end-to-end encryption, whether it be the supply chain that we work with. A lot of that work goes unnoticed and unappreciated. And frankly, like I said, if we do our jobs well, nobody knows that our stuff is here. So thank you for all that you do to make the world a better place. And then finally, thanks for your partnership. I think when I think about the word that describes today, and my folks here will laugh because it's going to be a C word from the people that attended my last meeting. C word is community. And when I think about kind of the dynamics of community, oftentimes it's partnerships inside Google and working very closely with the Chrome team and with the Android team and many other groups within Google that we have to partner effectively. It's also partnerships with many of you that are here, even competitors necessarily of Google, where we rise above the fray and actually have meaningful conversations about how we can move the industry forward, again, for the betterment of all. So community is really fundamental to what we're doing here. And so with all the thanks, I also have two asks. And this kind of reminded me of a quote from John O'Bacon, which is that, community isn't about what you get, it's about what you give. So I'm going to kind of adapt that quote a little bit and ask us for something, but so that we can all receive. Number one, I think there's a lot of great conversation that happened this week. I would love to see it continue. We have a Slack instance associated with Transparency.dev. So if you go to the website, there's a link to join that. Many of you are already in that Slack instance. There are plenty of channels to talk about everything from Sunlight to Trillion to research papers to a whole slew of things. So while it's wonderful to be together physically, continuing that narrative in the Slack channel as we go forth and kind of continuing this asynchronously, that's an ask that I have of all of you. And then second is that, we also talked about at a technical level, it takes all of us to be monitors. It takes all of us to be witnesses. It takes all of us to play those roles to keep each other honest. And so, where we see initiatives where, hey, I'm spinning up something new, how could I be a monitor? How could I be a witness? I think, even the Cloudflare example in the last Lightning talk is a great example of, hey, somebody steps up, builds something, as we can continue to do that for each other. Folks will look at that, folks will see it, and want to get more and more engaged. So we have to look out for each other in all of this. So, those are the two asks. Again, thanks for coming, and look forward to maybe the next one of these. I don't want to commit the team to it, but hopefully very, very soon, maybe next year we'll try to get everybody back together. But appreciate it. It's been a great week.
Great. Yes, very well said. Yeah, just final thank yous. I really like to thank the video folks. Peter and Gabriella have done a fantastic job recording all the talks. They're already up on the YouTube channel, so not just the live stream, but the individual talks. So let's give a round of applause to Peter and Gabriella.
And last but certainly not least, thank you to Tracy, who has gone out of her way for the last several months to coordinate all of this, all the logistics, and certainly a shout out to the team here at Google as well that helped to pull all this off. But we couldn't have done this without you, Tracy. So thank you so much.
Yes, my pleasure. All right, and with that, let's go into lunch.